Okay, so can I start, or is the recording started?
Yes.
Okay, okay. So I was supposed to say something about what I'm computing here, and okay, so what I'm using 28 CPUs for, etc. Um, and I plan to do this first very simple, okay, because most of you have not heard much about this topic anyway. Uh, so today I will probably only give some very basic introduction, and later maybe if we have time for another seminar, maybe I will become more specific and then say uh, a bit more in detail what I'm computing. Okay, but so let's try to start very basic things. So I'm working with knots, and you can think now. You must stop me if it gets too complicated, because I do not know how many of you know certain terms that I'm using. I would say I'm trying to make it simple, but maybe it's not simple enough. So I take some, let's say, smooth map from the circle to R3 or S3. So S3 is, you can think of S3 as R3, so three-dimensional space with one point at infinity, but you don't need to bother too much about this point at infinity. If you, okay, if S3 is too complicated for you, simply think about it as R3, so three-dimensional space. And let's say I consider this to be smooth something, and I consider this up to smooth deformations of the space. And I can
Why
do
do
this
you
not.
assume smoothness? Why doesn't it have to be
Yeah,
why
because then there are some very unpleasant examples if you do not assume smoothness. Okay, so
mm,
then if you assume that it's only continuous, then there are some ugly examples which are kind of counterintuitive. Okay, then it does not look like what you really want. Okay, so your idea is something like that you have some piece of rubber in three-dimensional space and you pull around it. Okay, so but if you assume only continuous, then you can have some problems with that. Okay, because then your continuous means that you can bend it and things like that, and then you get into some problems. This is why it is better to think of it as smooth. Okay, so
okay.
yeah. Uh, and so how okay, so now I can do this not only with one circle, I can have several circles. Okay, I can put a union of several circles embedded. So I mean without self-intersection. Okay, so it should really be an injective map. And the best way for us to think of this is by being represented by some diagram. So now what is a diagram? Okay, when you have something in three-dimensional space, you can project it onto the plane. So you can map it, okay? And then you lose one dimension, okay? Now you have two dimensions. Okay, and then this circle is mapped to some kind of a curve, okay, something like that. You can see my cursor, right? So you can have one curve, closed curve, you can have several closed curves. Okay. And then you lose some information because you project from R3 to R2. And in order to recover this missing information, you need something for the crossing. So I should say these crossings should not look like this. Okay, so they should be transverse. What does transverse mean? So this means the tangent vectors are not multiples of each other or something. Okay, so I do not want to have self tangencies and things of this sort. So crossing should look like that. Okay, and then you can distinguish which strand is above. So when you project, you lose one dimension, but in this one dimension, you know what is above and what is below. So you can indicate it by drawing the crossings like that. Okay, so here this strand is above, here this strand is above. Okay, and then you get a picture which looks something like that. Okay, and also I will need this maybe later. Sometimes I want to put an orientation on this loop. Okay, so I can say I run this loop in this way, or I can run this loop also in the opposite way. And of course, I want the orientation to be coherent. So I do not want once on the same loop to run once this way and then to run the opposite way, and then I collide here. So this is not allowed. Okay, so I just distinguish one way to run along the node. And if you have this, then you can sometimes distinguish these crossings with plus and minus. So every crossing will look either this way or this way up to rotation. Okay, and then this is what is called the sign of a crossing. I may need this a few times later, so I define this here. So you can have orientation, and of course you can reverse the orientation. So when you have orientation this way, I can simply turn the arrow around and I have it that way. Okay, so this is one thing I can do. The other thing I can do is I can also mirror. This means I change the orientation of the 3 space of the R3. Okay, so how can I mirror? I can mirror by mirroring the diagram in the plane. So let's say I will put here a vertical line, and then this is the mirror image with respect to this line. Okay, this is one thing I can do. The other thing I can do is I can mirror by simply turning all crossings around. I can mirror with respect to the dimension which I lose when I project. Okay, and then this means simply that when I have this, I make that, and when I have this, I make that. Okay, and now you see in this example, when I mirror with respect to the vertical line, I get this, and when I change all the crossing, I also get this. So I got the same. They are not always the same diagram, but I can by rotation turn the one into the other, so it doesn't really matter. So they always give me the same knot. And by the way, I need to also fix the names for a few things that I will consider later. So if I have a circle which can be mapped without any crossing, so a circle lying in the plane, then it's called unknot. And then if I have something like this, I call this a trefoil. And when I have 2 components, so I have 2 S1s, then for example, I can do that. Then it's called unlink, and I can do that. Then it's called the Hopflink. I may need this a few times. So now the question is, how do I classify this? So when can I deform one embedding into another? Okay, now I specify these embeddings in terms of diagram. Now there is a theorem which says the following. So if you have 2 embeddings which are equivalent in the sense that I can deform the one into the other, I can change their diagrams by a sequence of this type of moves. So there are 3 local moves. They are called Reidemeister moves, and so they look something like this. So for example, here I have a crossing, and I have one strand which passes above the crossing. And now on the left, it passes left. On the right, it passes right. So I can move this upper strand over the crossing, then it looks like that. Okay, now it's suggestive that this is a deformation of the knot. So this is some kind of moving in space. Similarly, if I have 2 strands like that, then I can put the one above the other, then I have something like that. And also if I have a strand of this form, then I can put a crossing on it, okay, in this way. And now, so I must say, when I draw this, this always is understood as a local move. This means this is not only one move, but it is a whole family of moves where I only draw what is different on the left and on the right. So for example, if I have something like this, then this means, let's say I put a small circle around it, and then I add something outside, which is the same everywhere. Okay, and then so when I add this outside, then I have something like that. Okay? So this is how this move here is supposed to be understood. This means it acts in some small piece of the diagram, and everywhere outside of this piece is the same. So for example, it can be this, but it is an infinite family of moves. Okay, and okay, these moves are now they're called Reidemeister 1, 2, 3. Okay, so the theorem says, if the 2 embeddings are the same, so if the knots or links are equivalent, there is a sequence of Reidemeister moves, and the opposite also. So it's an equivalence. Okay, and maybe I should say, okay, so this moves also plus mirror image. Okay, so I can of course take the mirror image of these diagrams, and then so with all crossing changing is also correct. Yeah. So. So and okay, and now the problem is if you want to classify this this kind of embedding, you have now a theorem. It tells you if I want to decide whether 2 diagrams belong to the same knot, there is a sequence of moves. But the problem is how long. Okay, and the problem is that if you use this move in this direction or this move in this direction, number of crossings goes up. So this means you're not in a finite space. Okay, so these moves can make the diagrams very complicated. So if you start from here to here, you may have here some diagrams which are much more complicated with many more crossings. Okay. And so the question is, how long should be this sequence? If you want simply to use a sequence of Reidemeister move to decide whether they give you the same knot, then how long should you how long sequences should you try? And now there are results about that, at least in special cases. One very basic case is I want to understand whether the diagrams belongs to the unknot. Okay, so I start with some diagram D and want to know, is this diagram D a diagram of the unknot? So this means I have a sequence of Reidemeister moves which turn D into that. Okay? Now the question is, how long is should this sequence be when I start with a diagram of n crossings? And there is a result. Okay, there's a concrete result due to Hassen-Lagarius, which says something like the length of this sequence is less than or equal something like 10 to 10 million or 10 billion or something times n. Okay, and now so when you put n is equal to 2 or 3, okay, then you get more than the number of particles in the universe to the power 1000 or whatever. Okay, so you see, this is not, I mean, this is not practically useful. So there is no computer is powerful enough to test you this amount of sequences. So, and this is only for the trivial knot. So for the unknown. Okay. So okay, but I mean, I should say there are attempts. I mean, the result is very general. So in practice, you can do this better, and there have been some attempts to use some algorithms like this to find this sequence. Okay, this is the problem of recognizing the unknot. When I have a diagram D, okay, to find the Reidemeister move that make it into that. Okay. So there have been some attempts, but you see from this kind of result that this is really very difficult. So there's not an easy this is not an easy computational problem. Okay. So maybe I will say something about this later. But okay. So now let me define, since I need this later, what is the crossing number? Okay, so now whenever you have a diagram, you can count the crossing. Okay, so for example, this has 0 crossings, and now this has 1, 2, 3 crossings. This has 2 crossings, and this has 0 crossings. So you can count the number of crossings. Okay, but when you have some knot or link, you have many diagrams, okay? And the crossing number is defined by the minimum of that. So this is the smallest crossing number of all the diagrams. Okay? So for example, when you start with the unknot, of course, the unknot has the diagram with 0 crossings, and there is no diagram with less than 0 crossings. So the crossing number of the unknot is 0. Okay, and now you can. So for example, if you take the trefoil, this has 1, 2, 3 crossings, and the crossing number is 3. But because every diagram of a knot with less than 3 crossings is so with 1 or 2 crossings is a diagram of the unknot. Okay, you can check it very easily. Okay, but so this is the argument behind that statement. Okay. For the Hopf-link, you can find that it is 2. For example, if you do something like this, okay, so 1, 2, 3, 4 crossings, okay, but I can remove this 1 crossing, so I can get back to the trefoil with 3 crossings. So this means this is a diagram with 4 crossings, but the knot of the diagram has 3 crossings. Yeah. So similarly, okay, now this went over the scanned piece, this knot, which I call figure 8. Okay, so this is the figure 8 knot. This has 4 crossings. Okay, it's 1, 2, 3, 4, and you cannot do with less. Okay, you can prove that it does not work with less. So the crossing number of this knot is 4. Now, okay, and another thing that I will need a few times is this construction of which connected sum. So this means the following: if I take some piece like this and some piece like that, and then I cut out a little bit from the left and a little bit from the right, and then I put a bend. Okay, and then I get another loop. So now this goes like that. Okay, and this is another way to form a new knot. So I have 2 knots, and then the result of this is the connected sum of these 2 is that. Okay, and this is called the connected sum. So for example, if you start with some knot and put the unknot, so you just have a loop, and then you connect with a bend this loop, then you do not really change anything. You can simply put this bend back, and then you simply have the original knot. So if k connected sum with 0, k connected sum with the unknot is k. You can think of this a little bit like prime numbers and multiplication. Okay, every real number is the product of prime numbers in a unique way. And the unknown is a little bit like 1, because when you multiply with 1, then you get the same thing. In some way, you can think of it in this way. So now here is already one very basic problem. Okay, so I have been talking about knot theory for 15 minutes to people who haven't heard much about knot theory before, but I can already formulate you a problem which is a problem of, I don't know, 100 years or something, and nobody knows how to solve it, except in special cases. Namely, the problem is, if I take the connected sum, does the crossing number add? Okay. So it is very easy to prove this is less than or equal. This is very easy, okay? But the problem is, when is it equal? In some cases it is known, but the general problem is open, and basically it has been around for 100 years.
Alexander, I have a question.
Yes.
So this connected sum, how is it precisely defined? Where should the second knot be connected to the first?
This is a good question. And the answer is, it doesn't matter. That's an exercise.
Okay, thank you.
So the statement is, whenever you have two diagrams and you choose some small pieces of the one on the other and do that, okay, then you always get the same. Okay, this is some basic exercise. Because you can, the idea of proof is that this thing here, you can make it very small. Okay, you can make it like a small bubble on this loop, and then you can simply move this along that knot. And then you go to some other place, and then you can blow it up again. Okay, and then you see that it doesn't really matter where you do this band connecting. Okay,
I see.
So this is
Thank you so much.
Yeah, so this is a well-defined operation. Okay, I mean, I should have said that. Okay, so this is this is already one basic problem. So okay, I will return to it, but I promised I wanted also to say something about braid. Okay, so what is a braid? How you can think of a braid? Okay, a braid is, let's say you have one board on the bottom and one board on the top, and you have a number of strings. Okay, and now they are connected. They are connecting one point in the bottom with one point on the top, and these strings can go through each other like this. But the condition is the strings always go up. Okay, and the bottom and the top are fixed. Okay, so this is like you nail it there. Okay, and then you do not move. Okay, so I can move the strings left and right. Okay, but I'm not supposed to move their ends, and of course I'm not supposed to cut the strings and okay, move the string through another or something like that. Okay, so this is how you can think of a braid. I will explain very soon what is the connection between this and knots. So, but for now, okay. So, braids they form a group. Is it clear what is a group? Okay, so this means this is a set, okay, with some operation which you can write it as a multiplication if you want. And the multiplication is given. You simply stack one braid on top of another. So usually instead of drawing this kind of picture, I will simply say, I will put these strings coming up on top and going in on bottom, and then I will put a box, which means that this box here, which I call beta, stands for something like that. Okay. So now I put the orientation always up, and then I can compose. I can put the second braid on top of the first, and then I forgot this intermediate line. Okay, and then I have an operation of multiplication. So, and with this, the braids form a group. Okay? So very often they are written in terms of this Artin generator. So what is an Artin generator? It is a braid with one crossing. Okay? So now, if you remember, here I said something about positive crossing and negative crossing. Yeah, and I use this concept also here. So I say, if I have a braid in which every strand goes just straight up beside the other, except I and I plus one, which cross positively, then I call this sigma I, and when they cross negatively, then I call this sigma I inverse. Okay? And it's very easy to see that when I multiply sigma I with sigma I inverse, I get simply the braid where everything goes up. These two crossings cancels because of that. Okay, and then I simply get the trivial braid. So and this element sigma I, they're called Artin generators. Okay, standard Artin generators, and they satisfy these relations. So they commute if their indices are more than one apart, and if they are one apart, then they satisfy this relation sigma I plus 1 sigma I is sigma I plus 1 sigma I plus 1. Yeah, and now you can see what this relation mean in this picture. So what does this mean? So this means something like this. If you have two pairs of strands where the indices differ by more than one, then all these strands are disjoint. Okay, this means that it's like you cross first here and you cross first there, but since the strands are disjoint, it doesn't matter. You can simply put this on top and this on bottom, and then you have it the opposite way around. So this is what this
I
relation
have a question.
Yes.
Is it the same as the permutation group over n letters?
Yeah, okay, I will come to this in a moment. The point is, yes, you have a homomorphism to that group. Okay, but the difference is that you see you distinguish this and that, right? So you okay? I will say something about this in a moment. Okay.
Okay.
So the commutation means first sigma and then sigma j is the same as first sigma j and then sigma I, because the strands are disjoint and I can pull this crossing against the other. So this is why you get this. And if you think about this relation, what does this says? This relation, if you draw it in this picture, then it looks like this. This is the same as that. Okay, and this is exactly, okay, this has exactly something to do with this move. This is a kind of a version of the Reidemeister 3 move in the braid group. Okay, so now it is known that you can understand this braid group in this way. So you have these generators and this have these relations. Is this notation clear? So is this clear what it means that I have a group on these generators and I have this relation? This means generators means I can build words in these letters, okay, arbitrary words in these letters and their inverses. And relation means whenever I have something inside some word which looks like this, I can replace it by that. And similarly, when I have something which looks like this, I can replace it by that. Okay? So elements in the braid group, the equivalence classes of words in these generators up to these local changes of words. Okay? So now, what is the connection between this and that? Okay, and the answer is there is this closure operation. So whenever I have a braid, I draw it again. You have strands going up, and then I put a box for these things that happens here inside. Okay, I can do the following. I can identify the end of the rightmost strand with the bottom, because I can simply put a string that connects it in this. And I can do it with every string. I can do it with n-1, with okay, until 1. Okay? And then I have this. And now, if you think about it, what is this? This is now you do not have strands anymore. They are closed, so they are circles. It can be multiple circles. It doesn't have to be one circle, but it can be multiple circles. But this gives you an oriented link. So it gives you something like that. Okay. So this is called closure. Okay, and Alexander, so not me. Okay, so this is Mr. James Alexander, who lived 100 years ago. He proved that every link is the closure of a braid. I write this hat operation for the closure. This means when beta is a braid, and I write for beta hat for the link which is obtained by closing. Okay, and James Alexander, so this is his family name. He proved that every link is the closure of a braid. So this means I can write every link in this form where beta is some braid. And from this you can define, I'll probably not use it often, but you can define the braid index. So what is the braid index? You simply count the number of strands of this braid beta for a given link. You see very easily that you can always make it more complicated, like for crossing number. Okay, for crossing number you can also make diagrams more complicated, so you can only add crossings. Okay, but you cannot always reduce. And the smallest number of strands, the smallest number of these things which come out for a given link is, do you see me?
I see your mouse, but not your face.
No, you're supposed to see my slides, because the frame around the window disappeared for some reason, and then I started worrying that. But you can see my note, right?
Yes.
Okay. So I can define I can define the braid index as the minimal number of these strings among all the braids that have a given closure link. So there, for every L, there are many beta, okay? And I can always make more complicated, but I can always not always make simpler. So I may not need this too often, but let me mention it here. So the important result about this braid is something like similar version of that. Okay, so here you see two diagrams are related if there is a sequence of moves. Yeah, and this is equivalent. So the important point, the important direction is this way. Yeah, when you see that this always change, it does not change, but you want to prove that if they are equivalent, then you can find these moves. And there is something similar here. Okay? So for braids, there is a similar theorem, which is called Markov Theorem. And it says when are two braids, when they give you the same link. Okay, and there are two operations. So which kind of correspond to the Reidemeister. So there are two operations. The one operation is conjugacy. Okay, is this clear what the conjugacy means? So this is a group. Okay, when I have an element beta and an element alpha, I can build alpha, beta, alpha inverse. Okay, so this is what is called the conjugacy in the group. Okay, now if you think about it again in terms of this picture, so what does this say? This says I put the alpha on the bottom and alpha inverse on the top. Okay, and so now what happens if you close? Okay, so close means you connect the strings, and now what you can do is you can take alpha inverse and you can slide this along this closed string so that it lands in the bottom. Yeah, so then you have, then instead of alpha beta alpha inverse, you have alpha inverse alpha beta. Okay, and now you can cancel. You can cancel in the group. You can simply cancel alpha inverse with alpha. Okay, and then you get beta. Okay? So it is very easy to see if the braids are conjugate, then the closures are the same. So this is the first move. Okay, this is a move within the same braid group, and then there is another move, and that move creates a lot of problems. And this is what is called stabilization. So obviously I can make braids more complicated. How can I do this? I can do this by adding this kind of extra crossing. Okay, so whenever I have a braid on n strings, I can make a braid on n+1 strings by doing the following. I add an extra string on the right, and then I add a crossing. It can be this way or that way. It doesn't matter. You can do it this way or that way. And it's very easy to see if you close, then the links are the same, because what happens if you add this and close it, then you get something like that. Okay, and now again this corresponds somehow to this move here. Okay, so you have a loop, an empty loop with a self-crossing which you add or remove, and this is exactly what you get here. So I can remove this loop and then I go back to that. So this is what is called stabilization. And Markov's theorem says that two braids give the same closure link if and only if they are related by a sequence of these moves. Okay. So again, the one direction is obvious. So if they are related by a sequence of this move, then the closures are the same, but the important is the converse of that. Okay. So, and now this then became very important because like for the construction of some invariants. What is an invariant, I will say in a moment. Okay. So so now you can change the problem of classifying links to the problem of you can try to do this via braids. Okay, so you can say I have a one not K1 and another not K2, and I want to know are they the same. What should I do? I find a braid for the one not, I find a braid for the other, and then I know that there should be some sequence of moves. Okay, but the problem is again that this stabilization makes the braids more complicated. Okay, again, this because it adds strings. Okay, and in general, you do not know how many strings you have to add. Okay. So conjugacy, I mean, the problem to decide where two braids are conjugate, this is solved. Okay, this is that problem has been solved long ago by Garside, and there are many algorithms. Okay, but this second move, the stabilization, that creates a lot of problems. Okay. And this is what, yes?
I haven't fully understood. If you're given a braid, then that means the number of strings is basically fixed, right? So
yes, but
how is it not?
So I mean the for the braid it is fixed, but for the closure it's not fixed.
I see.
Yeah, so you can have two braids with the same closure, but they do not need to have the same number of strings.
Okay, I see.
Yeah,
Thank
yeah.
you.
So
That's
I mean
important and
that is
subtle.
so it is like for diagrams. You can have two diagrams which represent the same node, but they do not need to have the same number of crossings, right? Because I can, for example, here you have these two diagrams. They represent the same node, but they do not have the same number of crossings. Okay, and something similar happens here. Okay, so here you have two braids which have the same closure, but they do not have the same number of strings. This one has one string more than that one. Okay.
I see.
Yeah. So I mean that is the problem. This means that I can make braids more complicated in the same way as I can make diagrams more complicated.
Right. And Markov theorem, this equivalence notion means refers to the closure of the braids or the braid?
Yes. Well, it says that the closures are the same if I can relate the braids by these moves, but this means that I must make braids complicated.
Okay, I see.
Yeah.
Thank you.
So it is similar story to this. Okay, this is a similar story to this. There is a sequence of moves, but the randomized, but the number of crossings may get up. Okay, and the problem is here similar. So there is a sequence of moves, but the number of strings may get up. Okay, so so this is a very complicated problem. So now let me come back to what was it Donghyun who was asking me this question. So there are some homomorphisms of the braid group. The first thing is you can build you can find a homomorphism into the symmetric group. So what does this mean? Symmetric groups means permutation. Okay, whenever I have a braid, I have a permutation because, for example, here I have a permutation of a string. 1 goes to 2, 2 goes to 3, 3 goes to 1, and 4 goes to 4. Okay, so I have a permutation. The braids permute strings, so I have a homomorphism from the braid group to the symmetric group. So the group of permutations. And what is the homomorphism? Okay, you can define the homomorphism in terms of this here. Okay, and what you do is essentially you simply forget the crossings. So you think really of this, you make this equivalent to that, and you make this equivalent to the transposition of element 1 and our I plus 1. So you can draw it in this way by you forget the crossing, and then you say this goes to that and this goes to that. Okay, so this gives you some homomorphism. It's very easy to check that this gives you homomorphism. So this is the permutation homomorphism. And another thing that you can do is you have a homomorphism to Z. And the homomorphism is now, when I write braids, I use multiplicative notation. So the operation is, I write it a dot, but Z I understand as an additive group. So the operation on Z is plus, okay? And the homomorphism is simply send sigma I to 1. What does this mean? Every letter is sent to 1, and then this means if you have some word, then you simply add the exponents of the letters. This is why I often call this exponent sum. So for example, sigma 1, sigma 2 to the minus 3, sigma 3, 1 minus 3, 1, it gives you minus 1. Okay. So this is called exponent sum. This is another homomorphism of the braid group. And another one, this works only for B4 to B3. So remember B4, so B4 has 3 generators, sigma 1, sigma 2, sigma 3. And B3 has 2 generators, sigma 1, sigma 2, sigma 1. Okay. And I can map this way, sigma 1 to sigma 1, sigma 2, sigma 2, and sigma 3 goes to sigma 1. This is a very well-known homomorphism, and this does not extend to any other braid group. This is a very special case of these 2 small braid groups that there exists this homomorphism, but this is sometimes useful. Okay. So and now, okay, I'm already so low on time, but